So my talk is actually very much in line with the two keynotes we heard this week. So it's about parallelism, heterogeneous, and generating efficient code kind of automatically. So this is joint work with Chris Finch, Sam Lindley, and Christophe Dubois all from Edinburgh. Okay, so the problem I want to talk about today is parallelism, obviously, but especially the kind of different types of parallelism we see nowadays. Different types of multi-core CPUs, GPUs, FPGA accelerators, and all of them, like programming them is really, really, really hard, right? And the main problem, I guess, is that people want to use them because they get performance from that, but optimizing the code for them is even harder than just get a correct program, right? And one of the main problems we want to address with this work is that the performance or the code you write is not portable. So you have to re-implement and re-optimize your code for every different device. I want to start by looking at a case study, and I will show a lot of OpenCL code, but I'm not expect anybody to understand it, at least not in the like everything. And the study is super simple. It's just reducing an array. So we want to compute the sum of all the values in an array, right? And Nvidia has a guide how they want OpenCL programmers to program their code. So they have 7 different implementations where they talk about 7 different optimizations you should apply to get very good, efficient GPU code. And one of the points in this reduction is that in OpenCL you need to have synchronization, obviously, somehow in this parallelism. And in OpenCL you can just synchronize globally if you stop what is called kernel, a function executed in parallel on the GPU. So for doing a parallel reduction, you inherently need 2 kernels if you want to get efficiency. And we're basically going to talk about the first kernel because that's the one which actually matters for performance. Okay? The first implementation they produce looks like something like this. Okay? And this is an unoptimized implementation of a parallel reduction. Okay? And I will briefly talk about the OpenCL programming model and some features which kind of programmers need to be aware of to write this kind of first version. Right? So this is a kernel which is modified with this kernel keyword, which is basically a function which is executed in parallel on a GPU or any parallel device, right? In OpenCL, there are different address spaces, which means you have to explicitly copy data over from this global memory, which is kind of the main memory storage. And for efficiency, you want to use this local memory, which is like the last parameter of the function, because this is a fast memory, which is kind of like a cache in performance, but you have to explicitly use it, right? And then because everything like this function will be executed by many threads, which are called work items in OpenCL, and you have these functions get local ID to actually get an ID which distinguishes you from all the other work items executing this code. And then you can group threads or work items into work groups. And obviously, to get correctness right in this parallel settings, you need memory barriers and this sort of thing to get it correct, right? If we now want to start to optimize this code and write different versions, and this is kind of the next version, and one of the optimizations they say is you should try to have threads which are kind of close to each other to execute the same code, right? So you basically change a bit here, like how this if works, to select kind of 2 different, like other threads kind of doing other work to get better performance. Another optimization they do is you interleave the addressing, which gives you better performance on memory accesses from the global memory. And you can actually increase computational intensity per work item, so every work item will do more work, and you actually have less threads overall. You can do some bits because of the execution model in OpenCL or in Nvidia GPUs, actually, they group 32 threads together, what they call a warp. And this will always be executed together on the GPU, so you can avoid synchronization inside of this warp, right? Which is implemented here in this version. Then you can start unrolling loops, and you can kind of extend actually the amount of work a single thread is doing even further, and end up with something like this, which is kind of the last version presented in this optimization guide from Nvidia. And the case study, basically, what this shows me is like, it's not obvious that the left unoptimized version, which I actually already don't find very pleasant and nice, actually relates anyhow to this fully optimized version on the right. So it's not clear that these 2 actually implement the same program. And it's not necessarily clear why the right one is faster than the left one, right? And to write either of these versions, but especially the one on the right side, you really need to understand these hardware details, like these warps and the different address spaces and so on and so forth, right? And so the question actually is, who is willing to invest in writing in these languages, right? So is it actually worth it, right? And the performance results clearly show yes. If you write these kind of naive first version, then you get very, very, very poor performance. But by doing these steps I showed you, you kind of gradually increase performance until you get something which is kind of decent, and actually in this case close to what kind of the Nvidia engineers write themselves inside of the cuBLAS library. And the performance factor here is a factor of 10, so you can't just ignore it because people usually do GPU programming because of the performance, right? But if you look at these OpenCL versions and run them on different architectures, so you run them on an AMD GPU or you run them on an Intel CPU, we actually get a very different performance picture, right? So that means on AMD, like the last implementation is worse than the second to last, right? On the Intel CPU, this warp optimization where you get the synchronization away is actually illegal because they are not grouped in this way, right? So the last three versions, they run, but they produce the incorrect result, right? Which basically lets me conclude the optimization we see, they are not portable in OpenCL. So you write specific versions like kind of tailored to one particular device, and that's bad. So the challenge for us here is how to achieve actually a portability not just of code as we actually have in OpenCL, but kind of performance so that we see kind of this picture for these types of devices as well. And this is what this talk is about. Okay, so our goal basically is to have this performance portable code, and the means how we achieve this is by use concepts from functional programming. So we basically start off by having a high-level expression which is built off of algorithmic primitives like map or reduce, and we lower this by applying rewrites where we know like kind of they are correct in the sense that the programs will always remain semantically equivalent, and we're rewriting these high-level expressions to something which is still functional but way closer to the OpenCL programming model. Okay? So in these low-level patterns or OpenCL patterns, you have something like map workgroup, which means I will map this or will apply this function to the entire workgroup. And then finally, we can generate OpenCL code from this. I will basically talk you now through the three steps of the three representation, like the high-level language, the low-level expressions, and then how we actually generate the code from this. Right? So the high-level expressions, which look very functional, so the reduction example we just saw becomes this one expression, kind of obviously, and we build them out of these algorithmic primitives, right? Which are very familiar to a lot of people, I guess, like map, zip, reduce, and we have something like split and join, which allow you to map these arrays, which I use the bracket annotation to specify here the type. So bracket of A means an array of type A, and we keep track of the size of the array and the types because we use this later on for doing memory allocation and other bits, right? So the split and join, for example, the split takes a one-dimensional array and adds a dimension by dividing it, right? And this helps us later on to decide how to actually map these computations to the hierarchical structure of having groups and threads and sequential execution in the OpenCL programming model. And we have this interesting function iterate, which has a rather complicated type because of the dependent typing which goes on, which basically applies a function multiple times to the same input array, or basically to the array and then to the output of its applying points. And now we can write these higher level programs, right? So we can write, for example, a dot product by saying we do a zip of two arrays, then we map the multiplication, and then we reduce it by applying the sum, right? And you can use these primitives to write other, like bigger expressions, like this GEMV, which is matrix vector multiplication, in a purely functional style, right? Okay, so now we know how to express these high-level programs, and now comes kind of the interesting bit, at least for me, is these middle bit, the rewrites, and kind of coming down to this OpenCL-specific functional representation, which is still kind of reduction, right? So we have kind of high-level algorithmic rewrite rules, right? Which are stuff like if I have a map of a function, I can also say I split the array in chunks of size n, and then I map a map of f to every chunk, which means I map inside of every chunk the function to every element. And then afterwards, I join to get back the same structure. Right? Or I can map fusion. If I have two maps, I can do it at once. Or for example, we have here reduction, which is kind of interesting because we express reduce in terms of map in this middle rule, which basically is a partial reduction, so we will not end up with a single element. But we use this kind of divide and conquer style rule, and the map now explains how we introduce parallelism in the reduction. Okay? And we have also a way to iterate a partial reduction, to do a bigger partial reduction, which we will later use to do an iterative reduction in OpenCL, which we kind of saw in the OpenCL implementation we saw earlier. Besides these algorithmic rules, we now also have OpenCL rules, which work on these OpenCL primitives. These kind of now reflect the low-level structure of how OpenCL works. So we have primitives like map global, which means I will map to every thread on my GPU, but we can also explore these hierarchy, which you can see on the right side, to first map stuff to work groups, and then to single threads inside of these groups, right? We have sequential implementations of map and reduce in OpenCL. We have primitives which kind of can copy stuff to different memory areas. And we have some primitive to do SIMD-style vectorization in OpenCL. So besides the high-level OpenCL rewrite rules, we also have OpenCL-specific rewrite rules, which kind of lower the implementation down to the OpenCL world. So for example, if I can see a map, I can choose to implement this now either by saying I want to use parallelism here, so I'll maybe use the map global, or I want to use sequential implementation here, so I use map sequential. Okay? But we can also use local and global memory, which are only legal if you're inside of a workgroup. That's why they're kind of tied to this map local. And we can see the vectorization rule, which, for example, says if I have a map, I can always decide to vectorize this map by splitting in kind of vector chunks and then apply a vectorized version of the function to every of these chunks, right? And then there's, for example, another rule where we can explain how to fuse a reduction and a mapping, which is kind of important for the dot product. Okay, that's kind of how we do, or how we express the rewriting, I should say. Like how we do the rewriting, I will talk about a bit later. But now I want to briefly show you how we actually then generate code from this representation. Code generation actually becomes very easy because all of these patterns are very explicit. So map global means I will write a for loop, which will actually be executed in parallel, because every single work item or thread will get different IDs based on these assumptions. Okay? So the interesting bit, or the interesting property now here, is that we have these rewrite rules and we can start applying them. And because we know they are correct, because we've proven correctness for them, we can start applying them to get different implementations for those high-level specifications. So we have reduce of plus, for example. We can start applying these rewrites and get different valid implementations from this, right? And we can start to do this by now fully search these spaces, right? And we implemented a very, very simple search strategy as kind of a first step in this direction, where we basically say we have the search tree, and for every node, we start applying all the rules which are kind of immediately possible, right? So this one, or this one, this one. And after we apply the rule in the first step, then we will start kind of sampling the subtree by randomly choosing rules to apply, generate code, execute the code, and then actually measure performance. And when we get back these feedback, we will choose the subtree with the highest performance and then repeat this process until we kind of find good implementations. And if you start running these, you can find, you start off by here, for example, that's a sum, so that's a reduction, but you have the absolute value you're reducing. You can find different implementations for Nvidia AMD GPUs and the Intel CPU, where, for example, the automatic search picked up somehow that the Intel CPU uses vectorization with a factor of 4, the AMD GPU uses vectorization with a factor of 2, and the Nvidia GPU doesn't use vectorization at all, right? Because it's not beneficial actually on this architecture. Okay? And these searches, to let them run and let them actually find implementations, these graphs, I should explain how to read this graph. So these graphs show all the small dots you can see are different versions we tried, and then on the left side you can see basically the scale of how fast they were, and the red lines connected the fastest version we have found so far. And we have basically evaluated roughly 70, 60, and roughly over 100 expressions to find implementations which are actually quite good, right? But these searches take some time, right? They take roughly an hour or so, okay? But the result we actually obtained from this shows really good performance against existing portable implementations. So here we have scale, asum, dot product, gemv, which are all in the like the BLAST implementations, and we compare here against the CL BLAST implementation, which is an OpenCL BLAST implementation written by AMD, and you can see that we either match or outperform this portable implementation, especially on the CPU, which is maybe not so surprising because the implementation has been written for a GPU, right? But if we actually look at each different hardware on its own, we can see that we can basically get the performance in these benchmarks which Kublas writes, like the expert programmer would write on Nvidia. We outperform AMD for some of the benchmarks, and we are kind of similar, for one benchmark way better, but for the others kind of similar, like what Intel writes with their MKL implementation of Kublas. Okay. Yes, and that brings me to my summary, which basically says this is an idea of first of all, I want to convince you that OpenCL code is not portable. Inherently, you write specific code for specific versions. And our approach tries to use functional ideas, functional techniques to get these high-level primitives. We get a kind of functional representation of OpenCL, and we rewrite the expressions to get actually performance portable code. And we kind of show that even a simple search strategy for this simple benchmarks can give you performance which is as good as you would write if you're an expert in the language, kind of for free. And that's it. Thank you.
Okay, questions?
So I really like how intuitive your search strategy is. So I'm wondering if you can clarify one little bit of intuition,
sure,
which is when you sort of randomly generate after that first rewrite selection, what's the intuition that random selection is actually going to choose the best first split?
Right. So we don't know, right? So that's what I'm saying. It's a simple search strategy where we don't actually know much. Right? The intuition here is that by doing this random subsampling, I would call it, of the subtree, we basically just make a decision on applying kind of the upper rule, right? And the idea is we apply this one rule and we try to sample, get a kind of representative performance of deciding which of the kind of these options we have at the kind of upper level makes sense. But obviously, we can kind of miss something here and not find the best performance possible or whatever, right? But at least for this benchmark, it worked out to be sufficiently fine, right?
So this is really great stuff. We've done some similar work, not for GPUs, but just for sort of multi-core stuff. And there we ended up looking at enough different optimizations that the search space got really huge.
Yes.
And so we had to start to get smart about how we did the search. And so some things that worked out pretty well were basically having like a greedy heuristic to sort of kick things off, like do as much fusion as you possibly can right off the bat, and like go data parallel to the right number of threads. But then after that, after that initial step, there's a good chance that you're actually not at the best point. And so then you want to do like a local search from there. So that's kind of what worked for us, and that who knows, that might help you guys when you start looking at larger programs or more optimizations.
Yes, thank you for the feedback.
Do you use any specific things in your specific to the GPUs? Like some of those numbers seem like magic numbers. Do you just kind of search for those, or do you put a bunch of those into your code so that you're picking kind of the right ones?
So we kind of design. I mean, first of all, OpenCL is a language designed for GPUs, right? And by